Our first topic will be about gravitational field and how the forces of gravitation affects us as humans. So here are the two equations we're going to look at today. The first one is if we're looking for the gravitational force on an object, then we are using the equation F. The gravitational force equals the mass of that object, and here the okay, I forget the word. Let's see if I can do that. That happens. So let's see, we have, I need to go a bit further up. So I have here the gravitational force. There we go. So let's see. So here are two things we have to look into. And you're going to say, well, this looks very close to what I already know. And it is F equals m times A. So if you look at Newton's law, the force on an object is the mass of that object times the acceleration of this object. Interestingly enough, when you look at the gravitational, at G here, which is the intensity of the gravitational field, this one here relates in many ways to what we have there. So let's see. So if I have the force on an object, let's say that this individual here weighs 100 kilograms. And here, when we have the gravitational field here, we have 9.8 Newton per kilogram. So this is the information we have right here. So the gravitational force on this human on the surface of the planet is the mass, which is 100 kilograms like this, times the gravitational field of the human at that place, which is 9.8 Newton per kilogram. And interestingly enough, we have here the units that are canceling. We end up with 100 times 9.8. We have 980 Newton. This is the force that we have on that human right here from Earth. So that's something to look into. Now, sometimes some people will say, well, if you have F equal m times A, and we have the acceleration, keep in mind that if you're at the top of a building and you are letting, let's say, what can it be? Like an acorn, for example, and you let it fall, slowly it will fall. And then the further and further away you are from the ground, it will accelerate all the way to the ground. And the fastest this object will be, keeping in mind that, let's say that there's very little air friction for the height of a building, then the maximum speed will be at the ground. So interestingly enough, what is the force of an object right at the beginning, just right on the surface? We can also say the force here on the object equals 100 kilograms, because we have the human here, times meter per second square. So negative 9.8 meters squares means that the object is accelerated downwards towards the center of the Earth. So here the force equals negative 980 here kilogram meter per second square. And interestingly enough, all of these units here are the same thing as a Newton. So this is how this formula has been working together. Now that brings us to the next equation I have for you, which is the universal gravitational law. So let's see what we've got here. This law, let's see if I can erase some of these one here. So the universal gravitational law says that if we have two objects, for example, in our solar system, we have the sun and the earth. We have the sun that is attracting the earth due to gravity. We have the earth that is attracting the sun due to gravity. So in between those two parts here, we have gravitational force between those two objects. So if someone wants to decide, okay, what will be the gravitational force, we can actually calculate that. And the equation is this one here. The gravitational force between two planets is here the universal gravitational constant, and it's always 6.67 times 10 to the negative 11 Newton meter square over kilogram square. We need to multiply this by the mass of the first object. So if I have the sun, it is here 1.99 times 10 to the power of 30 kilograms, times the mass of the other object, which will be 5.98 times 10 to the power of 24 kilograms, and that over the radius square. The radius, the average radius between the sun and the earth is about 1.5 times 10 to the 11 meters here. Now here it's interesting because we are looking at the force between two objects, and that force, the gravitational force, is basically has three portions. Has the mass of the two objects, mass of the sun and mass of the earth. And here this is earth, so I'm going to put an E right here. And the radius. The larger the radius, the denominator gets bigger, therefore the force decreases. And that's why as we have astronauts going away from Earth, it gets to a point in space, and because if they're traveling around the Earth, that the force is zero or feels like zero. And that's why we have a no gravitational field, and the astronaut can float in the International Space Station, for example. So here the big question is, can we calculate that? So let's see. So this is a big calculation. So let's see what we've got. So here we just have to plug in the numbers. So we have the force like this, which is equal to, here's the universal gravitational constant, which is 6.67 times 10 to the 11 Newton meter square kilogram square. You're going to say there's a lot of information here, but you'll see how it will simplify very soon. We're going to multiply by the mass of the first object, so the mass of the sun, 1.99 times 10 to the power of 30 kilograms, times the mass of the other object, which is here the mass of the earth, 5 times 98 times 10 to the 24 kilograms over, and we have here the radius between the two objects, which is 1.5 times 10 to the 11 meter, and this whole thing here is square. So this is the information we have at this point. So what did we do? We looked at the information that was available. We plugged in the information in the equation, and this is what we've got. Now here we can do some simplification and see what we can do right here. So let's see what are the calculations we can do. First of all, here we have the radius square. So let's see if we can do this. So when you are getting this number square, you multiply this number by itself. That means that 1.5 times 1.5 is 2.5. It's a bit less than this, is 2.25. If you have 10 to the power 11 square, then we're using the theory with exponents, of the exponents law. So when we have an exponent of an exponent, we multiply the powers. So here we have times 10, 11 times 2 is 22, like this. So let's see if we can change that for the denominator right here. 2.25 times 10 to the 22. Oh, this is in meters square. So here we're simplifying the information because there's so much here that we need to make it easier. Now we can here simplify the units. So if I have here meter square, but I also have meter squares at the denominator, these can simplify. We have kilogram square here, but we have here times kilogram and kilogram. So all the units, all the kilograms units here, here, and here will simplify. So there's only one unit left, which will be Newton here, which is great because the unit of the force is in Newton. So here it is one good thing. The next thing we're going to do here, this is a big number. And if you look at the calculator, it gets hard to put all the information. So here is my trick to make it easier. So because they're all multiplications and divisions, we're going to rearrange some of these numbers. So I'm going to start with the numbers that are easy to deal with. So we have 6.67 times 1.99 times 5.98, like this, divided by 2.25. So what I did now is I put all these first portions of these scientific numbers right here. So now what do I have left? I have all the powers with base 10. So I have here 10 to the power of 11 times 10 to the power of 30 times 10 to the power of 24 here over 10 to the power of 22. And the beauty with that is that it's simplifying the information that I have to put into the calculator. So if I multiply all these numbers here, let's see if I have done it. I had a calculator earlier. Perfect. So all these portions here, they are easy to do with a calculator. Equals 35 point, let's see, where's my calculator? 35.28. So about 28 like this times. So we took care of this first portion here. Let's see if we can work with the other part. We have times 10. So now we have to look at the exponents. When you look at the different laws of exponent, when we are multiplying powers with the same base, we add the powers, and when we divide, we subtract. So that means that here, if I am to look at all of these, I have 10 to the power of 11, plus we have here the powers here of 10 to the power of 30 and 10 to the power of 24. And here, because I'm dividing by 10 to the power of 22, I'm going to subtract 22 right here. So let's see if I can now do this without even a calculator. So if I have 24 minus 22, this gives me a 2. If I have negative 11 here and 30, so that is a positive 19. And 19 plus 2 is 21. So here I was able to do all of these in my mind here. And then all I have to do now is add the unit I had, which is newtons right here. Now, interestingly enough, if I look at my number here, I have 35. When you have scientific numbers or scientific notation, we want a number between 1 and 9.9. And therefore, I'm going to take this decimal point and moving this way. So I have 3.528 times 10. I'm going to add 1 here, Newton. So this is the gravitational force here between the sun and the earth. Now, what's interesting here, you can use this for many things. So if you are to be in a physics lab and you have 2 small objects, you can do your calculations. Your numbers at the end will be much smaller because we're working with few kilograms compared to numbers of kilograms that are planetary size. So that's something to look into. Next, someone would say, well, can we do the same about a person on Earth? You certainly can. But what you will notice is that the mass of the Earth compared to the mass of a person, the difference is so big that it doesn't make a dent in the numbers. So here, if you remember this equation here, we're multiplying 2 masses. And if you have the mass of the Earth, which is 5.98 times 10 to the power of 24, the mass of this person here is so negligible compared to this big number that is the same thing as if you have this one right here. And the distance between here, between the radius of the center of the Earth and the surface is a much smaller number than the radius between the sun and the person, and therefore you end up with a number that is reasonable and a bit different. So we can use this equation here for any two mass, keeping in mind that if there's a difference between the mass of small objects or the mass of a person compared to the mass of a planet, for example. These are things to think about. In the meantime, we have a lot of things we can learn on this channel. So I'm going to put here a link to another video about our solar system, and let's see you there.